Okay, so we were looking at AX transpose, and I told you guys to see if you could come up with some, like, alphabet soup made out of A's, X's, and transposes that would equal this thing. And you guys came up with this really nice size-wise argument. Like, if A is m by n, and x is n by 1, then the result of that multiplication is going to be some, I guess, well, it's going to be a vector, right? It's going to be a vector, I don't know, I'll call it y. It's m by 1, right? And then the transpose of that is going to be some vector that is 1 by m. Then you all looked at the X transpose and A transpose and realized that A transpose... Whoa. Hey. Hey, stop. Chill. I don't even know what you're barking at. Just barking at the idea of A transpose, X transpose. Look at how upset she is. Totally makes sense. Why would she be barking at this? Yeah, there's no reason to think that this would even make sense, right? Because X transpose is a 1 by n vector. Really a row vector, right? And A transpose, well, if A was m by n, then this is n by m. And there's only one way to make this make sense, and that's if m is 1.
Which, like, chances are it isn't.
Yeah, which, like, chances are it isn't, because that would indicate that we're not talking about a matrix A, we're talking about a vector A. And then why would I write this way? You guys with me? So this thing probably doesn't even work. So it can't be this. So then you're like, well, the other obvious choice is to consider X transpose times A transpose, and...
Oh my.
Okay. Excuse the technical difficulties there and the vertigo. So, at the very least, X transpose A transpose would be the right size. Right? So we're like, okay, so probably this is X transpose A transpose. Now, being the right size is not an argument that this thing actually works, right? It's just a heuristic. And you might kind of Occam's razor your way through this thing. Occam's razor is not really quite as simple as it sounds. Oh, which interestingly is a counterexample to Occam's razor. That's cool. Okay. Think about that. Turn your brain off for a hot minute. In order to actually demonstrate this, let's take a look at A as though it were rows. So I'm just going to take my matrix A, and I'm going to say it's got rows in it. How many rows is my matrix A going to have in it? Let's see. Yeah, we said A was m by n over here. So that's m rows. With me on that? And then I'm multiplying this by my vector x, right? So x right now is a column vector. And the result of doing this is going to give me 1. So this is AX. How do I multiply this? How about simpler? Which picture am I going to use right now? Am I going to use the row picture or the column picture?
The row picture?
Yeah, I'm going to use the row picture because I wrote rows. It's a clue. So when I pick this vector x up, I'm going to turn it sideways and drop it onto the rows, right? That's the row multiplication picture. So I'm going to get a vector. This is going to be the vector AX, right? And the vector AX is going to be made out of row 1 dotted with the vector x down to row m dotted with the vector x. You guys all with me on that? Okay. So that's AX. So that means that AX transposed, right, is going to be a row vector And that's this vector A, 1 by m over here, right? And that row vector is going to be row 1 dotted with x for the first coordinate, row 2 dotted with x for the second coordinate, and at the end here we're going to have row m dotted with x m. Oop, not x m, just m. You guys with me? Okay. Now my task is just going to be to take x transpose times A transpose and just check and see if that's the same thing. You guys see that? Like, I have a sneaking suspicion. So I can either fiddle this thing around a little bit, or I can just calculate x transpose times A transpose and check and see if they're the same. You guys good with that? So let's just calculate x transpose times A transpose quick. So x transpose is a row vector, right? So that's kind of x transpose. I've written this out in a slightly screwy notation. I'm kind of aware of that. You guys good with this thought, though? And then I need my matrix A transpose written out here.
So it would be like, in turn entries have what would normally notate as column run be row 1.
Good. Yeah, the first column of the matrix A transpose is the first row of the matrix A. You guys see that? So this is, I'm going to write row 1, but it's a column because I transposed the matrix. You guys all with me on that? So we're going to have all our rows scattered out through here, and they're now the columns, and there are still m of them. You guys with me on that? So this is going to give me a vector. What's that vector going to be?
It's going to be row 1 dotted with x, row 2
Yeah,
dotted with x, and all the way to row n dotted.
You guys see that? The first entry is going to be me picking row 1 up, twisting it sideways, and dropping it onto the vector x. So I'm going to get a vector. Try to figure out what size to write there. I started a row vector. You guys see that? Is that correct?
It's possible. I believe so.
Okay, so what sizes were these things? Oh, I know what size this thing's gonna be, right? It's gotta be the same size as this thing at least. Oh, sorry, the same size as this thing at least. You guys see that? So I know it's gotta be a row vector. That's kind of cool. And now I'm gonna pick these up. So the first entry is gonna be row 1 dotted with x. And the second entry
Row 2 dotted with x.
is going to be row 2 dotted with x. And we're going to continue that until we get to row m dotted with x. Cool. So not only are they the same size, they actually are the same thing. Which is not hugely a surprise, right? Like, I had this good, strong suspicion before, but now I know for sure. You guys good with this? That line of reasoning makes sense?
Yeah.
Okay, cool. Because your next task... Oh, you guys got lucky. Your next task is going to be next time.